Hello, welcome back. This is Calc 1 by Dr. Oz. Today we're going to start a new section called Indeterminate Forms and L'Hopital's rule. This is going to be 2 videos in total. In the first video, I'm going to try to achieve the course learning objective of recognizing limits that produce indeterminate forms. So essentially, you're going to try to see what kind of different indeterminate forms we have, and we had a similar discussion when we were talking about the limits in the beginning of calculus. So we're going to revisit that topic, but with the knowledge of derivatives. So and then in the second video, we're going to learn how to apply the L'Hopital's rule to evaluate certain limits. All right, let's start. All right, when we started learning about the limits in the beginning of calculus, we encountered different cases where you had very cold, indeterminate forms, and those were the forms of the form 0 over 0 or infinity over infinity. And when you run into one of those cases, we generally try to use algebraic techniques to simplify the expression so that we can get rid of the 0 over 0 or infinity over infinity type forms. Just to give you an example, looking at this limit here in this example, we have x approaching negative 1 of the quotient 2x squared minus 2 divided by x plus 1. And when you plug in negative 1 right away, just to see what the behavior looks like, and you right away get 0 over 0 type indeterminate form, but we also know that 2x squared minus 2 can be written as 2x squared minus 1, and in fact x squared minus 1 is the difference of squares, so I can also split that into 2 linear factors, and as you see that these factors are essentially the same, so we divide them out. And then this quotient is equivalent to 2 times x minus 1. And once you write that down this way, you can pass the limit without any problem because you have no 0 over 0 indeterminate form anymore. And then you get, by plugging in negative 1 here, you get negative 4 as the result of the limit. So this was one thing that we used earlier in the beginning of calculus. And here's another example where you have infinity over infinity type indeterminate form. So as you see that as x approaches infinity, 3x squared minus 1 is going to approach infinity, and so is the bottom. So in this regard, we learned a shortcut, essentially saying that if you have the top and the bottom having the same order, well, in this case, both are quadratic, so the limit is going to be the ratio of the leading coefficients. And in this case, leading coefficients are 3 and 2. And the limit value is 3/2. And in fact, you can also handle this problem by factoring out the highest order of the factor at the top and the bottom. So you have 3 minus 1 over x squared at the top. And in the bottom, you have 2 plus 1 over x squared, and we can perfectly cancel out the x squared terms, and then we're down to 3 minus 1 over x squared, and in the bottom you have 2 plus 1 over x squared. Now we can pass the limit because we don't have any infinity over infinity anymore, because this term now approaches 0. 1 over x squared approaches 0, so the whole limit approaches, the limit value is going to be 3/2 essentially. So here, algebra was very helpful to rewrite those expressions to go around the indeterminate forms. And in the next slides, you will see that we're going to introduce what's called L'Hopital's rule to handle these limits without relying on algebra. And in this slide, I really want to talk about other indeterminate forms. You may have not experienced some of those. I think we talked about infinity minus infinity type indeterminate form, even 0 times infinity. But there are some others like 0 to the power 0, 1 to the power of infinity, and infinity to the power of 0. These are all indeterminate forms, and you may have a limit value at the end once you run into one of those cases, or you may not have the limit existing. Okay, so you conclude that limit doesn't exist. So you have to sort of like investigate each case carefully. And one of the common mistakes is, in fact, writing that 0 to the power of 0 is 1, or 1 to the power of infinity is 1, or the 0th power of infinity is 1. These are wrong because these are in the limiting sense. This 0 is not number 0, but it's something very close to 0. This infinity is not a number, but it's something big, but we don't know how big it is. So when you take the power of that, and the power is very close to 0, you don't know the actual behavior or where it converges to. You don't even know if it converges to something. Okay, so there are some other forms as well, like infinity plus infinity, but these are determined forms because something big plus another something big, that's going to take you to plus infinity. So even though they look like indeterminate, in fact they are determinate. Or something big, very negative, something big, very negative added to that is going to be something very big, negative. Okay. And 0 to the infinity, that's likely to be 0, and 0 to the minus infinity, which is 1 over 0 to the infinity. Since this goes to 0, then the whole thing is going to blow up, so that's in fact going to converge to plus infinity. Okay, so these are different types of forms that are determinate. All right, just notice that this infinity minus infinity and infinity plus infinity are two different things, by the way. This one is indeterminate and this one is determinate, because here you don't know what infinity minus infinity is, because both infinities could be large. Both infinities could be at the same level, so the difference could be 0. But most likely it's indeterminate because the infinity concept for each term here could be totally different. But infinity plus infinity for sure, adding a big number to another big number is going to be a big number. Okay, so let's move on. You can also use some other algebraic techniques for in fact the same algebraic techniques for transcendental functions. Like, for example, if you're looking at this limit e to the 2x minus 1 divided by e to the x minus 1, when you pass the limit, so it's going to be e to the 0 minus 1, e to the 0 minus 1, that's going to take you to 0 over 0. So, well, these guys are not polynomials, but it doesn't mean that you can't factor them. In fact, e to the 2x minus 1 is the difference of squares. So I can rewrite e to the 2x minus 1 as e to the x squared minus 1 squared. So when you have difference of squares, you can split that as e to the x plus 1 and e to the x minus 1. And the bottom is already e to the x minus 1. That allows you to cancel out e to the x minus 1 from the top and the bottom, and you're down to e to the x plus 1, and this expression here is a very nice expression to pass the limit, because after you pass the limit, it's going to be e to the 0 plus 1, which is exactly equal to 2. So using algebraic techniques, that you use for polynomials and rational expressions, could be also applicable for transcendental functions and even trigonometric functions. So you have to just check the given expression in terms of you may factor or not. And remember that there are primitive ways to check what the limit could be once you run into an indeterminate form. And obviously one of the best things to do is to look at the limit. For example, if you have the limit as x approaching 0 of e to the 2x minus 1 over x, well, just plugging in 0 for x is going to take you all the way to 0 over 0, which is an indeterminate form. So if you graph this function for x min and x max in the neighborhood of 0, like in this case -4 and let's say 2. Okay, so in your calculator, you can graph this function, and you can actually visually observe that around zero, the function values approach 2 from the left and right. So the limit value, no wonder it's going to be 2. Okay, so graphing is one of the best ways, obviously, to check the limit values, even in the case of like indeterminate forms. And the second primitive way to check the limit values is just having a table of sample values. You start taking sample values around 0 with some increments. Obviously, you start with 10 to the minus 3, and 10 to the minus 2, 10 to the minus 1, and 1. And you go all the way on the other direction symmetrically as well. So all you do is evaluating the function at those test values by using your calculator. And as you see that you are increasing to 2 here on the left, and as well, you are now decreasing to 2 on the right, and no wonder you can conclude in this case that the limit is in fact equal to 2. Again, one primitive way is to graph the function, and the second primitive way is to look at the table of sample values. And you will see now that we're going to introduce the L'Hopital's rule, and you're going to sort of like bypass all of these primitive ways of checking the limit, including the algebraic way of checking the limit, which is like canceling out some of the terms, rewriting the expression using algebra, like in this case, using algebra techniques to simplify the expressions. You were going to sort of like detour all of them, and you're going to use the power of the L'Hopital's rule. All right, let's stare at the description of the L'Hopital's rule. Let's say like we have 2 functions which are differentiable on an interval containing c. C is the point where you check the limit for. So you are looking for differentiability at c, or around c, not necessarily at c, but around c. So we assume that g prime is not equal to 0 for all x in the same interval, and g prime of c may be undefined. That's fine, right? That's okay. So if the limit of f of x over g of x as x approaches c produces the indeterminate form 0 over 0. So in fact, we're going to expand this inclusion. We're going to also include infinity over infinity, or all other types of combinations of infinity over infinity into the game. But to start with, let's say like you have 0 over 0 type indeterminate form. Once you pass the limit here, then that limit that you're after is equivalent to the limit, the same limit, except that you take the derivative of the top and derivative of the bottom separately. Okay, so it's not like we're applying the quotient rule or something. We're just applying we're just finding the derivative of the top, derivative of the bottom. So then we pass the limit again. This is a brand new limit, but turns out that L'Hopital's rule says that those limits are equal. Okay, and obviously these limits are equal as long as the second limit exists, right? If this limit doesn't exist, then we can't talk about the equivalency. Okay, and even if you say like it's infinite, that's fine. All right, so this L'Hopital's rule also applies to all sorts of infinity over infinity type indeterminate forms, and some of the infinities could be minus. So I'm talking about all sorts of like combinations of infinity over infinity type indeterminate forms. So you see the strength of this technique, because all you're doing is taking the derivative of the top and the bottom. You don't need to worry about the algebra anymore. Okay, so keep taking the derivatives, and as long as this limit exists, then the limit value is going to be the limit value of the original limit. And in fact, in certain cases, you can keep going. Let's say like you still have, let's say like you have 0 over 0, and you still have 0 over 0. That's fine. And this time, I'm going to look at f double prime divided by g double prime. If this limit exists, then this limit as well is equal to this limit as well as this limit. Okay, so this is a very, very, very strong result. So and we're going to apply it to different examples. And before I move on to the next example, here is a quick remark. When we talk about like limits from the right or left, we can still use L'Hopital's rule as long as we have 0 over 0 or infinity over infinity. And obviously, once you take the derivatives of the top and the bottom, this limit should exist in some sense, or it's infinite. So the take from here is that once you have sighted limits, so you're approaching C from the left or right, and if you run into 0 over 0 type indeterminate forms, as long as the limit exists or infinite, you can apply the same strategy, same rule, L'Hopital's rule, applying to your case. And this is the example we have been working on in the beginning, all right, since the beginning. So e to the 2x minus 1 divided by x. We graphed this function. We looked at the table of sample values. We cannot really use algebra here because the top is transcendental and the bottom is polynomial. There's nothing to cancel out. So, well, all we're going to do is first to conclude that this limit is 0 over 0, which is in fact true because we checked out before. E to the 0 minus 1 divided by 0 is 0 over 0. All right, so both functions are differentiable at 0. Just take the derivative of the top, which is 2 times e to the 2x. Okay, the chain rule applies. And the derivative of the bottom is just simply 1. Okay, so now I pass the limit again. Let's see what it is gonna spit out. So if you pass the limit, this is going to be 2 divided by 1, which is exactly equal to 2. So it's awesome that we bypassed the graphing business here, that we had the limit values approaching on the left and on the right, you're approaching to 2. In fact, this is even better, right? So the limit value was 2, and we also checked this by table of sample values. So now by using the idea of the L'Hopital's rule, just in as you see, like 1-2 steps to get down to the same result. All right, here's another case of infinity over infinity type indeterminate form. So we have done 0 over 0 with the previous example. So let's check. So as x approaches infinity, ln infinity is going to be approaching infinity. And x is already approaching infinity, so we have infinity over infinity type indeterminate forms. Okay, don't worry about it. No algebra, no graphing, no table of sample values. All we're going to do here is to pass the limits, but this time we're going to take the derivative of the top and the derivative of the bottom separately. So ln x has the derivative 1 over x, and x has the derivative 1. So if you look at this division, this is like 1 over x essentially. So now if this limit exists, the value of the limit is the value of this limit, the original limit I start with, that I conclude first that it's indeterminate. All right, well, as x approaches infinity, 1 over x is going to approach 0. There you go. So since this limit exists, I go back and then conclude that this limit as well approaches 0. And to sort of like confirm yourself, why don't you graph ln x over x and visually make sure that ln x over x approaches 0 when x's get larger and larger. And here's the graph of ln x over x. So I put the x-min to be somewhere close to 0 because for 0 and for x is less than 0, this is not defined. The function is not defined. Okay, and I try to increase the function values. As you see that the values approach 0 because they get closer and closer to the x-axis. So graphing helps obviously, but as you see that in this case, when you increase x's, in other words, as x gets larger and larger and larger, the corresponding values approach all the way to 0. Right, this is already a long video. Let's finish this video here, and in the next video I'm going to continue with the L'Hopital's rule and other applications. So I'll see you in the next video. Bye.